Before talking about the reaction, let's start the video with what are enols and enolates. Enols are compounds with hydroxyl groups in alkene molecule. Enolates are the conjugate bases of enols. Put it simply, it is an anion form of enols. Enolates usually form when alpha hydrogen of carbonyl group is subtracted. These enolates are a way to form carbon-carbon bond from the carbonyl compound. The typical alkylations of carbonyl compounds are as following. First, the formation of lithium enolates of ester by using lithium diisopropylamide. Then the alkylation of enolates. This reaction introducing new groups into the alpha position of carbonyl compounds. Side note, LDA is not so stable for storage, hence it usually made fresh in the laboratory before reaction by mixing diisopropylamine and butyl lithium in THF at low temperature. Reaction using LDA usually undergo at -78 degrees Celsius. This temperature is used for the stability of enolate and avoiding side products. One of the problems with ester-enolate is self-condensation, which is an ester-enolate reacted with the starting ester. This problem occurs when not all the starting ester have completely converted to enolate form. Thus, one of the solutions is to add the ester to LDA solution slowly. Hence, all the ester will form enolate, so there is no excess ester. Another tactic is to use bulky R group, such as third butyl, to discourage attack at the carbonyl group. Remember, the bigger the group, the larger is the steric hindrance. One example here is the successful reaction of third butyl ester with butyl iodide. First, the reaction with LDA forms the lithium enolate. Then, attack on butyl iodide forms the product. To perform alkylation reaction on carboxylic acids, two equivalents of LDA are used. The first one to make carboxylic anion, and the second one to make the enolate. Then, the electrophile is introduced to the reaction. If we use LDA with aldehyde compounds, it will still form enolates. However, this reaction is not fast enough, so there is still starting aldehyde present, which leads to self-condensation reaction. So, to alkylate aldehyde, we have the following alternatives: enamines, aza-enolates, and sillyl enol ethers. Enamines are formed when aldehydes or ketones react with secondary amines. For example, here is pentanol reaction with diisopropylamine in acid. Then, allyl bromide is introduced on the subsequent step. Lastly, imine here is hydrolyzed to form the aldehyde. While enamines are good enough, they are only weakly nucleophilic, so the electrophile must be reactive. If we need highly nucleophilic, aza-enolates are the solution. The formation of aza-enolates require primary amines. For example, here is third butylamine reaction with aldehyde in acidic condition. First, it forms imine. Then, treatment with strong base forms the aza-enolate. After that, electrophile, for example benzyl chloride, can be introduced. Lastly, imine can be hydrolyzed in acid to form aldehyde. The last alternative is sillyl enol ethers. reacting aldehyde with trimethyl sillyl chloride will form sillyl enol ether. This sillyl enol ether is good for reaction with SN1 reactive electrophiles such as tertiary alkyl halides. With the help of Lewis acid, titanium tetrachloride, tertiary carbocation is formed. Then this carbocation can be attacked by sillyl enol ether. Then sillyl enol ether can be cleaved with halide anions to form aldehyde. The alkylation of ketones can be performed using strong bases like the one with esters. However, the problem with ketones is there are two possible deprotonation spots. This enolates formation can be controlled thermodynamically and kinetically. The thermodynamic control is based on alkene principle. Since enolates are basically alkenes, the more substituent on the alkenes, the more stable they are. Hence, using 2-phenylcyclohexanone as the example, there is more conjugate enolate with alkene bond into the phenyl substituent than the other position. The other possible control is kinetic. LDA is a bulky and strong base, thus it likes to attack more acidic and more accessible proton of a ketone. Less substituted carbon is more acidic and also more accessible or less hindered. Hence, enolate is formed on this side of ketone.